The capacitor is a passive component built for one highly specific job: storing electrical charge and the resulting energy. Energy is held entirely through the physical tension of an electric field, avoiding the chemical dependencies found in a standard battery. In its resting, neutral state, the device consists of two conductive plates. At this point, both plates hold an exactly equal number of free electrons. When connected to a voltage source, that balance breaks. The source pulls electrons away from one plate, pushes them through the external circuit, and forces them onto the opposite plate. Because the plates are separated by an insulating dielectric, no electrons actually cross the physical gap. Instead, one plate becomes negatively charged, leaving the other equally positive. This creates a potential difference. Invisible lines of force form between those opposite charges, concentrating an intense electric field directly within the insulating material. If disconnected from the source, an ideal capacitor holds on to that imbalance, acting as a temporary electrostatic reservoir ready to release its stored charge. The capacitor operates as a physical trap, securing energy within the invisible tension of the electric field. The measure of this storage ability is called capacitance. Specifically, it is the amount of charge the device can store for every unit of voltage applied across its plates. This chart illustrates the defining equation, C equals Q over V. Capacitance is a constant ratio. As the applied voltage changes, the total charge stored scales in exact proportion. The base unit for this measurement is the farad. 1 farad represents a capacitor storing exactly 1 coulomb of electrical charge when pushed by 1 volt of potential. In practice, storing a full coulomb at 1 volt requires massive physical dimensions. 1 farad is so large that electronics work almost exclusively in much smaller fractions. You'll typically find values in microfarads, 1/1,000,000th of a farad, or picofarads, which are 1/1,000,000th. Precise circuit design depends on converting between these metrics. While the math defines the ideal ratio, the actual capacity is strictly bound by the physical dimensions and materials used to build the component. This model illustrates the physical variables that dictate capacitance: plate area, distance, and permittivity. Capacitance is directly proportional to plate area. A larger surface accumulates more charge. However, as plates move closer together, the distance variable in the denominator decreases. This inverse relationship means that reducing the gap tightens the grip of the electric field and increases the capacitance. The dielectric constant of the insulating material also plays a role, measuring how effectively it concentrates lines of force compared to a vacuum. Compressing these components introduces a safety constraint called dielectric strength. This is the maximum voltage the insulator can withstand before breaking down and allowing current to punch through. Moving plates closer together to increase capacitance simultaneously drops the breakdown voltage. You cannot shrink the gap indefinitely without risking physical failure. Even before a total breakdown, insulators are imperfect. Over time, electrons slowly migrate through the dielectric, a process called leakage current that drains the stored energy. Every capacitor design is a calculated compromise between high-density storage and the risk of electrical failure. Manufacturers use different dielectric materials to suit specific circuit needs, with mica and ceramic being the most common rigid designs. Ceramic capacitors utilize materials with massive dielectric constants to achieve high capacitance within a small disc or surface-mounted chip format. Plastic film capacitors take a mechanical approach, rolling thin layers of plastic and metal foil into a tight spiral to pack a vast surface area into a cylindrical housing. Electrolytic capacitors use an ultra-thin layer of aluminum oxide as the dielectric. Because the gap is so small, they can achieve massive values, exceeding 200,000 microfarads. Connecting these polarized components backwards causes a short circuit that boils the electrolyte, leading to expulsive venting of gas and foil. Variable and trimmer capacitors allow for fine adjustments after assembly by manually changing the overlapping area of the plates to tune the circuit. The choice of dielectric, from ceramic to tantalum, is the primary factor determining a circuit's frequency response and power stability. Wiring capacitors in a parallel topology effectively sums their individual plate areas. In this arrangement, every capacitor sees the same voltage, but each stores an amount of charge proportional to its individual capacitance. This sequential arrangement in series effectively increases the total dielectric separation between the outermost plates. Because the total gap has expanded, the overall capacitance drops. The total combined capacitance in a series string is always less than the smallest individual capacitor in the group. Network topologies allow for the creation of specific capacitance and voltage ratings that do not exist as standalone components. In a DC circuit, an uncharged capacitor acts as a short circuit to any instantaneous change in voltage. Once it reaches full charge, the electric field is fully established, and the device acts as an open circuit, blocking steady-state direct current. The transition between these states is not instant, because moving physical charge into the field requires a finite amount of time. This exponential rise occurs because, as the capacitor charges, its own internal voltage pushes back against the source, slowing the rate of charge. We calculate this rate using the product of resistance and capacitance, the RC time constant. Mathematically, this specific curve results in a 63% change in voltage for every time constant interval. Following this progression, it takes exactly 5 intervals, the transient time, to reach 99% of the final charge. During discharge, stored energy is dissipated through the resistor as the plates return to an equalized state. By pairing resistance with capacitance, the geometry of the plates becomes a precise tool for timing and time delay applications. Alternating current prevents a capacitor from ever reaching a steady-state open condition because the continuous reversal of polarity keeps the charge in motion. Because the highest rate of charge movement occurs when the voltage is passing through zero, the current waveform peaks exactly a quarter cycle, or 90 degrees, before the voltage wave. This phase shift creates capacitive reactance, the frequency-dependent opposition a capacitor offers to the current. As the frequency increases, the capacitor has less time to build up an opposing voltage, meaning reactance drops and high-frequency signals pass with ease. At low frequencies, the capacitor has ample time to charge and push back against the source, creating high reactance that effectively blocks the signal. This duality allows the capacitor to sort and filter electrical signals based entirely on their frequency. On this amplifier circuit board, you can see these various principles in action, with ceramic chips and large electrolytic cans performing distinct roles. Near the power input, large capacitors serve as supply filters. They absorb fluctuations from rectified AC to create a steady DC rail. The capacitor recharges on the voltage peak and discharges slowly into the circuit, resulting in a small sawtooth pattern called ripple voltage. Coupling capacitors sit between amplifier stages to allow AC audio signals to travel through, while blocking the DC bias voltages. Bypass capacitors are used to short high-frequency noise and transients directly to ground, preventing them from affecting sensitive integrated circuits. Technicians troubleshoot these boards with an oscilloscope to verify that each component is providing the correct reactance. If an oscilloscope detects DC voltage leaking through a coupling capacitor into the next stage, it indicates a failure of the dielectric. Beyond audio, capacitors govern timing in logic circuits and store binary data in computer memories, where the presence of a charge represents a logical 1. From smoothing power to processing digital data, the capacitor remains the fundamental geometric manipulation of electric fields, enabling modern electronics.